So what it led to was a number of major changes in our thinking with respect to things like motors. You couldn't put motors in a magnet, those kinds of things. So we found some relatively easy but expensive solutions. We use ultrasonic motors, which we buy off the shelf. They're expensive to say they're off the shelf, but it was a good solution. We were surprised by some things. We thought good old-fashioned aluminum would be non-magnetic, but in fact it may be non-magnetic, but it does affect the performance of an MRI machine. So we had to cast aside some of those ideas, and we used a material called PEEK. Just to go back a couple of slides, this is PEEK. It's a form of carbon fiber, and so these arm booms are made out of PEEK material. So a lot of the structure of the arm, which isn't, by the way, is known as the neuroarm, are made out of PEEK, and so it does not have any impact on the MRI machine. So what you see here is the assistant surgeon. This is the regular microscope used in the OR at the table. The arm is under the draping here, so it is not a very good shot of it. It uses fairly standard tools. You can see it doing its thing in the brain here. And here is the surgeon at his workstation. And so this in itself is a very novel piece of equipment here. What we did was take the regular output from a surgical microscope, and we digitized it and reconfigured it back at the workstation, and we were very pleasantly surprised that we could get the same resolution and the same quality of image in this artificial microscope as the real optical microscope. So that was a huge issue that we worried about, but it really worked for us. So this piece of equipment is in use every week. It's been through extensive Canadian trials. It's moving ahead now into where we've been asked to make some changes to it to make it more commercially viable, and that process is now underway. And so we're kind of heading towards that stage of this project. So a couple of things to go back to the SPDM, because this stuff is so interrelated. On the main arm, sorry, I used an acronym then, I lost you. SPDM is the two-arm robot. On this arm, we introduced force moment sensing. So the force moment sensing is this round thing here, the end of the end effectors. So what that gave the astronaut was an artificial sense of touch. When we progressed to this robot, we put force moment accommodation in. So what force moment sensing was our first step into haptics. So the medical world wants haptics. That was our first step. Force moment accommodation means if you're performing an operation robotically, let's say this is designed to pull a box off and push a box on. If you're pushing the box on and you're beginning to feel the load building, force moment accommodation will sense the load, feed it back into the robot, and change the solution of the robot so you keep the loads down and you don't overstress things, you don't damage what you're trying to fit. And so it was that. Having done that, we were then able to make this system a fully haptic system, which has worked really well. It has 2 degrees, it's a two-arm system, as I said before, 6 degrees of freedom. I mentioned the auto microscope. And so that was our first, and I think the big thing we learned about this was miniaturization was not as tough as we thought it was going to be. You just stick to the engineering principles, and we just worked our way through it. And I'd have to make a comment here that we don't consider ourselves to be inventors. We consider ourselves to be an applications company. We don't consider that we're inventing things because we don't invent things that don't have an application. So we have maybe a little bit of a different mindset to a startup company that's obsessed with inventing something because you have to succeed. So I would class us as applications engineers. And so then we've moved on to other things in medical. We're working with Dr. Anvari and his company into MRI-guided therapies. So we have one application we've done some experimental work. We're moving into development trials. We're looking at what other applications it can be applied to. All kinds of ranges of biopsies, and also what other medical processes it can be applied to. We're also working with Sick Kids Hospital in Toronto. There are many problems with newborn babies. Babies are born with deformities that you wouldn't imagine. For example, the windpipe can be connected to the bowel, those kinds of gross deformities. Some of those things have to be dealt with before the baby is born. Some of them can be dealt with immediately the baby is born. So we're working on some systems with sick kids to automate some things to make these kinds of surgeries easier to do. So when you're operating on a full-term baby, you're operating inside a grapefruit. That's the volume you have. And so imagine doing suturing with a tool that's outside of the body inside a grapefruit. These tools are this long. It's almost impossible. It takes probably 1 hour to get one suture done. And this is at the end of a 6-hour surgery, so it's a pretty exhausting situation. We're also working with the Children's National Medical Center in Washington. And so to go back the full circle here, we've now moved on to autonomy. Every robot we've ever built, we've always had an automatic mode, but now we've moved into the field of autonomy. And 3 or 4 years ago, we worked with the Boeing company and DARPA, and we created an experiment in space where there was a spacecraft in space that had a fault. And so Boeing built a spacecraft to fire into space with robotic arms on that we produced. And the whole idea was where autonomy comes into this is once these two, we knew where the spacecraft with the fault was. We knew where the orbit of the Boeing spacecraft was. So we were allowed one 16-bit command to tell the spacecraft to go and find the spacecraft that was failed, attach itself to it and fix it. So through that 16-bit command, that unleashed layers of software in here that autonomously completed the repair, and it repeated it, and it completed it successfully. So what we're working on now is autonomy in the medical field. So particularly right now in the area of sick children, anything we can do to make, to ease what the surgeons are having to do given the confined space. One thing I would say we're doing differently with some surgeons want a robot to do the whole process. So for example, the brain surgeon on the neuroarm wants to do every aspect of a piece of surgery using the neuroarm and every aspect of a piece of stereotaxy. Some surgeons don't want to do that. They want to look at a surgical process and say, I'm really struggling with this 10-minute piece in the middle here. That's what I want you to solve. And so in the case of sick children right now, we're working in the latter mode where the problem areas of a piece of surgery have been analyzed, and we've honed in on the particular areas that they're really struggling with. So we're focused on those kinds of things. So it depends what surgeons want. Of course, it will affect commercialization in the end. Other surgeons may want to do the same piece of surgery in a different way, but we don't really have any control over that. So anyway, that was the story, a historical concept and how we've moved into surgery, and we're trying to move into a more commercial area in surgery, but right now we're in the depths of R&D, and we have 4 or 5 different projects on the go. So, if there's any questions? Okay.